The notion that normalization layers are an indispensable component of modern neural networks has been a long-standing assumption. This research reveals that transformers can achieve comparable or even superior performance without normalization, leveraging a surprisingly straightforward technique. Dynamic Tanh is suggested, a simple element-wise operation that replaces normalization layers in transformers. It is inspired by the observation that layer normalization in transformers often yields Tanh-like, S-shaped input-output mappings. By integrating Dynamic Tanh, transformers without normalization can match or surpass the performance of their normalized counterparts, often without the need for hyperparameter tuning. The findings validate the effectiveness of Dynamic Tanh across a range of settings, including recognition, generation, supervised, and self-supervised learning, as well as computer vision and language models. These results challenge the conventional wisdom surrounding normalization layers and offer new insights into their role in deep networks. In a bid to bridge the gap between the geometric similarity of normalization layers and the scaled Tanh function, a paradigm-shifting approach, Dynamic Tanh is proposed. This innovative technique can seamlessly replace traditional normalization layers, offering a more adaptive and dynamic solution. By leveraging the learnable parameter alpha, Dynamic Tanh scales the input tensor X in a manner that is tailored to its specific range, effectively addressing the issue of varying input scales. The Dynamic Tanh layer is defined as follows: Dynamic Tanh X equals gamma asterisk Tanh alpha X plus beta, where alpha is a learnable scalar parameter that dynamically adjusts the input scaling based on its range. This is the essence of the Dynamic Tanh operation, which allows for a more nuanced and context-dependent scaling of the input. The parameters gamma and beta, which are learnable per-channel vectors, serve a similar purpose as those used in normalization layers, enabling the output to scale back to any desired range. In essence, Dynamic Tanh can be viewed as a separate affine layer, but for the purposes of this discussion, we consider it an integral part of the Dynamic Tanh layer, much like normalization layers incorporate their own affine components. To gauge the efficacy of the Llama 7B model in conjunction with RMS norm and Dynamic Tanh, a comprehensive benchmarking exercise is conducted. The assessment focused on the total processing time required for 100 forward passes, inference, and 100 forward-backward passes, training, utilizing a single sequence of 4,096 tokens. The results reveal the time required for each RMS norm and Dynamic Tanh layer, as well as the entire model, when executed on an NVIDIA H100 GPU with BF16 precision. Notably, the findings indicate that Dynamic Tanh layers exhibit a substantial reduction in computation time compared to RMS norm layers. This trend is also observed under FP32 precision, underscoring the potential of Dynamic Tanh as a viable choice for network design optimization, particularly in scenarios where efficiency is a primary concern. Layer normalization is a technique used in deep learning to normalize the activations of each layer in a neural network. The main idea behind layer normalization is to normalize the activations of each layer by subtracting the mean and dividing by the standard deviation of the activations, element-wise, for each layer. This is in contrast to batch normalization, which normalizes the activations of each layer by subtracting the mean and dividing by the standard deviation of the activations, element-wise, for each mini-batch. Layer normalization is indeed a common technique used in transformer models, particularly in the encoder and decoder layers. The LN layer's dual role in both linear transformation and nonlinear value squashing can be understood by examining the behavior of token and channel activations. To illustrate this, it can be visualized the distribution of points grouped by tokens and channels, respectively. Upon examining the left two panels of each token's activations form a straight line, with the slope varying across tokens. Tokens with smaller input ranges tend to exhibit smaller variance, leading to a larger slope in the straight line due to the normalization layer's division by a smaller standard deviation. Collectively, these straight lines form an S-shaped curve reminiscent of a tan function. In contrast, the right two panels reveal that different channels exhibit drastically different input ranges, with only a few channels, e.g., red, green, and pink, displaying large extreme values. These channels are subjected to the most pronounced squashing by the normalization layer. By examining the behavior of token and channel activations, we gain insight into the LN layer's ability to perform both linear transformation and nonlinear value squashing. This dual role enables the LN layer to effectively normalize activations and facilitate the learning process. In the realm of computer vision, the performance of various architectures is a subject of ongoing research. This study focuses on the ImageNet 1K classification task, a benchmark for evaluating the efficacy of deep learning models. Two prominent architectures, Vision Transformer, VIT, and SeoNVNXT model are trained. The selection of these models is motivated by their widespread adoption and distinct computational paradigms. VIT relies on attention mechanisms, while SeoNVNXT employs convolutional operations. From the figure, it shows that there are no major differences across two model architectures on Dynamic Tanh and layer normalization. The investigation of diffusion models revolves around the deployment of three distinct variants of the diffusion transformer, DIT, architecture, namely B, L, and XL, on the ImageNet 1K dataset. Notably, the patch size is optimized at 4, 4, and 2, respectively, for each model. In the implementation of DIT, we leverage the affine parameters of the layer normalization layers for class conditioning, mirroring the original DIT framework. However, we introduce a novel modification by replacing the standard normalizing transformation with the tan, alpha x, function. Following extensive training, we evaluate the performance of our Dynamic Tanh models using the Freshet Inception Distance, FID, metric, with the ImageNet reference batch serving as the benchmark. To evaluate the efficacy of Dynamic Tanh in conjunction with Llama, a series of experiments involving four distinct model variants, 7B, 13B, 34B, and 70B are conducted. These models were pre-trained using the same protocol as Llama, with the notable addition of a learnable scalar parameter appended to the initial embedding layer. This modification allowed us to dynamically adjust the value of alpha, a critical component in the Dynamic Tanh framework. The pre-training process took place on the piled dataset, a vast repository of 200 billion tokens, which served as the foundation for our experiments. By leveraging this extensive dataset, we aim to create a robust baseline for evaluating the performance of Dynamic Tanh in comparison to RMS norm, the default normalization layer employed in Llama. It demonstrates that Dynamic Tanh achieves comparable performance to RMS norm across all four model sizes, underscoring the effectiveness of this approach. The loss curves show that there are very similar trends across all model sizes, with training losses closely aligned throughout training. The investigation into the default setting of alpha equals 0.5 has revealed a nuanced relationship between this parameter and the performance of large language models. While the default value often yields satisfactory results across various tasks, we have discovered that fine-tuning alpha 0 can lead to significant improvements in LLM efficacy. To explore this phenomenon, they pre-trained each Llama model on a substantial 30 billion token dataset and compared their training losses. The results have yielded two crucial insights. In a groundbreaking experiment, it successfully trained cutting-edge neural networks, specifically transformers, without the need for traditional normalization layers. This achievement is made possible by Dynamic Tanh, a straightforward yet powerful replacement for normalization layers. By introducing a learnable scaling factor alpha, Dynamic Tanh adjusts the input activation range, effectively taming extreme values through a smooth, S-shaped Tanh function. Despite its simplicity, Dynamic Tanh remarkably replicates the behavior of normalization layers, yielding models that not only match but often surpass their normalized counterparts in various settings. Our findings fundamentally challenge the long-held assumption that normalization layers are indispensable for training modern neural networks. Furthermore, this study sheds new light on the inner workings of normalization layers, a fundamental building block in deep neural networks, and paves the way for further exploration of their mechanisms.